Good morning. We continue with our lectures on computer-aided engineering design. We have been discussing B-spline segments and curves. This is lecture number 26. We will discuss normalized basis splines and their properties today. Normalized B-splines. They are more popular than regular B-spline basis functions. A normalized B-spline basis function is given by n sub k sub I, a function of t, which is equal to ti minus ti minus k times m k I t. In a sense, if we multiply the regular B-spline basis function by its entire knot span over which it is spanning, ti minus ti minus k, we get the normalized basis function. It is very easy, as I mentioned before, for me to remember the expression for m sub k sub I of t. So m k I t is equal to t minus ti minus k over ti minus ti minus k times m k minus 1 I minus 1, a function of t, plus ti minus t over ti minus ti minus k times m k minus 1 I t. Now let's substitute for these m's over here. So mki of t will be nki of t over ti minus ti minus k. This relation comes from here. Likewise, m k minus 1 I minus 1 t will be n k minus 1 I minus 1 t over ti minus 1 minus ti minus k. Ti minus k is I minus 1 minus k minus 1. And then m k minus 1 I is n k minus 1 I over ti corresponding to the last knot minus ti minus k plus 1. This is I minus k plus 1. We can simplify this relation to get nkit equals t minus ti minus k over ti minus 1 minus ti minus k times n k minus 1 I minus 1 of t plus ti minus t over ti minus ti minus k plus 1 times n k minus 1 I of t. What we have done here is, if this factor comes in the numerator here on the right hand side, this factor gets cancelled with this factor and this factor here. So finally, normalized basis splines can be defined as follows. N1i, which are the order 1 normalized splines, a function of t is equal to delta I, such that delta I is equal to 1 for values of t belonging to closed ti minus 1, comma, ti open. This essentially means that all values of t will include the value ti minus 1, but will not include the value ti. For all other values of t not belonging to this interval here, n1i is equal to 0. This is for order 1 normalized basis splines. For order k normalized basis splines, where k is greater than 1, we have the recursion relation that we have seen before. nkit equals t minus ti minus k over ti minus 1 minus ti minus k times n k minus 1 I minus 1 t plus ti minus t over ti minus ti minus k plus 1 times n k minus 1 I of t. Now this normalized basis spline, as you would know, is non-zero for values of t in between ti and ti minus k. Here I am going from right to left. For all other values of t not belonging to this knot span over which nki stands, this normalized spline is 0. In some sense, the normalized basis spline will derive all properties of your general basis spline function mkit. Just that the only difference between the two would be that of the factor ti minus k. Let's look at some properties of normalized basis spline functions. So in the previous lecture, I had mentioned that it is important for you and me to be comfortable in sketching these basis spline functions and normalized basis spline functions. If you're comfortable in sketching them, you don't need to remember these properties. All you would need to do is simply work them out. And we'll see that today. The first one, nki of t is a degree k minus 1 polynomial in t. K is the order of the normalized B-spline basis function. So naturally, k minus 1 will be the degree of this polynomial. You would also note that nki of t is not a pure polynomial. Rather, it's a piecewise continuous composite polynomial. I would want to take you back to the definition of B-spline curves or segments. A B-spline curve of order k has to be k minus 2 continuous throughout. This is the second property, non-negativity. For all I, k, and t, n, k, I, t is non-negative. This is something that we have not seen before, but the recursion relation that we had derived in the previous lectures allows us to visualize this property. Let's try to give an informal proof. So in a given knot span, ti minus k plus 1, and so on up till ti, notice that these knots are arranged in ascending order. We would realize that n1i of t is equal to 1 for values of t belonging to closed ti minus 1 open ti interval, and n1i of t is equal to 0 for all other values of t. In a sense, n1i of t is equal to or greater than 0 in ti minus k ti, which is a parent interval here. If that is so, then we can say something very similar about this order 1 normalized basis function. n1 I minus 1 of t is equal to 1 for t in ti minus 2, ti minus 1, and n1 I minus 1 is equal to 0 elsewhere. Likewise, n1 I minus 2 of t is equal to 1 for values of t belonging to the interval ti minus 3, ti minus 2. Ti minus 3 included, ti minus 2 not included. And n1 I minus 2 is equal to 0 for all other values of t here. These two statements lead us to the following observation. n1 I minus 1 of t is equal to or greater than 0, and likewise n1 I minus 2t is also equal to or greater than 0 in the parent knot span ti minus k, ti. Where are we heading with this? Let's see. N2i, as you would know from the recursion relation, will be a weighted linear combination of n1 I minus 1 and n1 I. To be more precise, n2i of t will be equal to t minus ti minus 2 over ti minus 1 minus ti minus 2 times n1 I minus 1 t plus ti minus t over ti minus ti minus 1 times n1i of t. Now, we have seen previously that n1 I minus 1 is equal to or greater than 0 in the parent interval ti minus k ti. And likewise, n1i also behaves in a similar fashion. Now, let's look at these weight functions here, which are linear, as you would realize. Of course, n2i is defined to be non-zero in the interval ti minus 2 ti, and it's going to be 0 for all other values of t. Now, if you look at these weight functions here, t minus ti minus 2 over ti minus 1 minus ti minus 2 will be equal to or greater than 0. Why? Because I've already mentioned before that these knots are arranged in ascending order. So ti minus 1 is greater than ti minus 2, and values of t lie between ti minus 2 and ti. So the numerator is going to be greater than 0, and the denominator as well will be greater than 0. Again, if we look at this factor here, ti minus t over ti minus ti minus 1 will be greater or equal to 0 again. Why is that? T is smaller than ti. Maybe t can also be equal to ti, and ti, of course, is greater than ti minus 1. So this would make this factor equal to or greater than 0 for values of t belonging to the interval ti minus 1 ti. Now, when I say that this would be equal to 0, I mean in the limiting sense. Notice that we are using the open interval here. The value of t can be as close to ti as possible, but not equal to ti. You would want to keep that in mind. Well, what do we observe? So we have seen that for values of t in between ti minus 2 and ti, n1 I minus 1 is greater than 0 or equal to 0, and 1i is greater than or equal to 0, and these weight factors are also equal to or greater than 0. Naturally, n2i will be equal to or greater than 0 for t lying in the interval ti minus 2 ti. We can use similar arguments and show using mathematical induction that nki of t is equal to or greater than 0 for values of t in between ti minus k and ti. I would want to take you back to our previous lectures. Recall, we had made a few comments about mki of t. We had said that this is equal to 0 for t greater than ti. This is equal to 0 again for t smaller than or equal to ti minus k, and integral ti minus k to ti mki of t dt was equal to 1 over k, because mki t dt was designed to be standardized. So if we look at the bell-shaped characteristic of this function, we had worked on this part for values of t greater than ti. We had worked on this part for values of t smaller than ti minus k, and we had shown that the area is non-zero. If you recall, we had never talked about the non-negativity of this function for values of t in between ti minus k and ti. It is the recursion relation that allows us to see that mki of t, or for that matter nki of t, is non-negative in this range of t. In a sense, nki of t is greater than or equal to 0 for all t belonging to closed ti minus k, ti open. Let this be an exercise for you to show that indeed the normalized B-spline function nki of t is equal to or greater than 0 for, in fact, all values of t ranging from minus infinity to plus infinity. In particular, for values of t in between ti minus k and ti, this B-spline function is non-negative. Let's take a look at an example. Let's work with uniform knot span. T0 is 0, T1 is 1, T2 is 2, T3 is 3, and T4 is 4. This line here would correspond to N11. The last knot is T1, and this is of order 1 or degree 0. It has to be a constant. Likewise, this blue line here corresponds to N12 of t. The green line here corresponds to N13 of t, and the magenta line here is N14 of t. Last knot is T4, the first knot is T3. All these normalized basis functions, they stand over a single respective knot span, as you would observe. Now this triangle corresponds to N22 of t. It's a linear interpolation between N11 and N12. It satisfies the definition of a spline. It is of order 2, meaning it is of degree 1. That would imply that it has to have position continuity throughout. So there would be 3 junction points, junction 1, 2, and 3. If you observe, N22 will be 0 here. There would be a position continuity maintained here. It will be non-zero. In fact, it will be increasing in the first knot span between T0 and T1. There will be position continuity here. Notice that slope is discontinuous. And then N22 will be decreasing in the knot span T1, T2. And finally, at this junction point, or rather from this junction point, N22 will be 0 for t greater than 2. This here is N2, 3, t, a linear combination between N12t and N13T. And this here will be N24T, combination of N13T and N14T. This is a quadratic normalized basis function N33 of T that combines N22 of T and N23 of T. This one here is N34 of T. This combines N23 of T and N24 of T. And finally, this normalized basis function that stands over the knot span T0, T4 is N44 of T. We continue with the properties of normalized basis spline functions. Nki of T is a non-zero polynomial in Ti minus k Ti. This should be closed interval and this should be open interval. This is very clear. This comes from the standardization condition that the area under the basis function Nki of T is non-zero. The next one, and this is an important one. I would want your attention here. On any span closed Ti, Ti plus 1, at most P order P normalized B-splines are non-zero. Let me show you an example and then discuss a general case on the board. We start with a case which has the knot span Ti minus 4, Ti minus 3, Ti minus 2, Ti minus 1, Ti, Ti plus 1, Ti plus 2, Ti plus 3, and Ti plus 4, all arranged in ascending order. And an interval of importance is this one here, Ti, Ti plus 1. Let's sketch an order 4 normalized basis function. The last knot will be Ti plus 1. The first knot will be Ti minus 3. This is N4 I plus 1 of T. As you would see, this function is non-zero in this interval. What is this function? It stands over 4 knot spans, 1, 2, 3, and 4, and ends at the knot Ti plus 2. It has to be N4 I plus 2 of T. How about this one? Again, standing over 4 knot spans and ending at knot Ti plus 3. This is N4 I plus 3 of T. And finally, we have N4 I plus 4 of T. Now notice that all these normalized basis splines are non-zero over this knot interval. If I wish to sketch any other normalized basis function involving this interval here, Ti, Ti plus 1, I'll have to either end that basis function at Ti, or we'll have to start a basis function from Ti plus 1. In a sense, any other basis function that I draw will have to be 0 over this knot span, Ti, Ti plus 1. We see here, in case of an order 4 basis spline function, that about 1, 2, 3, and 4 order 4 basis spline functions are non-zero over the knot span Ti, Ti plus 1. Let me now explain a general case on the board for you. So let me have this interval of importance Ti, Ti plus 1. Let me extend this to the right and to the left. And let me work with order P normalized basis functions. J would be any, not Tj, at which npj would end. If I start with not Ti and sketch a normalized basis function, this would end at Ti plus P. And this B-spline here will be nomenclated as N P I plus P of T. Of course, NP I plus P of T will be non-zero over this span here. Now, if I sketch another B-spline basis function, normalized of course, in a manner that it ends at Ti plus 1. So I'll have to sketch this thing backwards. The starting knot will be Ti plus 1 minus P. And this knot here will be NP I plus 1 of T. Now let's try sketching a few more of these normalized basis functions of order P. For example, Ti minus P plus 2. If I start from here, I will end at Ti plus 2. Ti minus P plus 3. If I start from here, I'll end at Ti plus 3, and so on. All of these will be clearly non-zero over this knot span. So in a sense, all order P normalized basis splines starting from NP I plus 1 of T and ending at NP I plus P of T will be non-zero. You might want to count how many of these are. NP I plus 1, NP I plus 2, NP I plus 3 up till NP I plus P. You would realize that these are P normalized B-splines. In general, for any R, NP R of T is greater than or equal to 0 in the knot span closed TR minus P up till TR. If closed Ti plus 1 open is contained in closed TR minus P open TR, there should be one order P B-spline with Ti as the first knot and one with Ti plus 1 as the last knot. We have seen this before. So R minus P equals I and R equals I plus 1 would provide a range for such normalized basis spline functions, implying that R would go from I plus 1 up till I plus P, and they would be P normalized B-spline basis functions. Now, this is one of the properties that would provide local control, specifically local shape control for B-spline curves. Let's look at the other one now. This is again important, and I would want your attention on this one. Partition of unity. The sum of all non-zero order P basis functions over the span closed Ti open Ti plus 1 is 1, no matter what the T value or what the parameter value is. Let us revisit the example in the previous slide. So we had sketched 4 of the order 4 normalized basis functions, n4i plus 1, n4i plus 2, n4i plus 3, and n4i plus 4, all functions of t. And we had seen that these basis functions were non-zero over the non-span Ti plus 1. What this property of partition of unity says is that all these 4 basis splines will further sum to 1 for values of t in between Ti and Ti plus 1. Let me work this out on the board for you. We have the general recursion relation for nki of t, and that is equal to t minus Ti minus k over Ti minus 1 minus Ti minus k times n k minus 1 I minus 1 of t plus Ti minus t over Ti minus Ti minus k plus 1 times n k minus 1 I of t. We are interested in adding these 4 normalized basis functions, each of order 4, n4i plus 1, n4i plus 2, n4i plus 3, and n4i plus 4. Let's use this recursion relation to figure what n4i plus 1 is first. So I have t minus t. Now for I have I plus 1. For k, I have 4. So this would be I plus 1 minus 4. This is I minus 3 over t minus t I minus 3 times n3, k equals 4 in our case, and I equals I plus 1 in our case here. So this would be I of t plus Ti plus 1 minus t over Ti plus 1 minus t I plus 1 plus 1, which is I plus 2 minus 4 I minus 2. And this is n3 I plus 1 of t. How about this one here? An easier way for us will be to start indexing I by I plus 1, because here I is getting incremented by 1 each. So I can copy this relation from top to bottom with I as I plus 1. Let's see how it works. So this one here will look like t minus Ti minus 2 over Ti plus 1 minus Ti minus 2. I'll have to be a little careful here. This is n3 I plus 1 of t plus Ti plus 2 minus t over Ti plus 2 minus Ti minus 1 n3 I plus 2 t. Let's see if this is correct. I minus 3 to I minus 2, I to I plus 1, I minus 3 to I minus 2, I to I plus 1, I plus 1 to I plus 2, I plus 1 to I plus 2, I minus 2 to I minus 1, I plus 1 to I plus 2. Seems okay. How about the third one? T minus T, I minus 1, Ti plus 2 minus T, I minus 1, N 3 I plus 2 of T plus Ti plus 3 minus T over Ti plus 3 minus Ti, okay, times N3 I plus 3 of T. And finally, we have T minus Ti over T I plus 3 minus Ti times N 3 I plus 3 T plus Ti plus 4 minus T over Ti plus 4 minus Ti plus 1. I have to increment this also by 1 times N3 I plus 4 of T. Now let's be careful in observing something here. There are some common terms, N3I plus 1, N3I plus 1. And look at the denominator here, Ti plus 1 minus Ti minus 2, Ti plus 1 minus Ti minus 2. I can club these two terms together. Likewise, N3 I plus 2 is common here, and the denominator Ti plus 2 minus Ti minus 1 is also common here. So I can club these two terms together. And if you see here also, a similar thing happens. So I can club these two terms together. I'll try not to make a mess of this as much as I can, because I will be erasing a few terms and adding those parts here. Let's see how good I am at that. So let me first add this term here and then erase it. So I'll have plus T minus Ti minus 2 over Ti plus 1 minus Ti minus 2. And this is N3 I plus 1 of T. I'm erasing this now. Okay. Now I'm going to be clubbing this term with this one here. Let me add this thing on the left. I'll have plus, this would be T minus Ti minus 1 over Ti plus 2 minus Ti minus 1, and curly parenthesis here. So I let go of this term and let me take this term here. This would be T minus Ti over Ti plus 3 minus Ti, again curly parenthesis. And I let go of this term here. Let me remind you that we are adding these four normalized basis functions. Now let's look at this term here. What do we have? Denominator is common, and this t cancels with this t here. And if you see, ti plus 1 minus ti minus 2 is the same as the denominator. So in fact, this term will be 1. Likewise, what do we have here? This t cancels with this t, and we have ti plus 2 minus ti minus 1. Again, the same as the denominator. So this term here is again 1. How about this term here? Something very similar. This t cancels with this t. Ti plus 3 minus ti is the same as the denominator. So this term again is 1. So in the entire addition here, we have this term plus n3i plus 1 of t plus n3i plus 2 of t plus n3i plus 3 of t plus this term here. Now let me clear the board and express this addition once again. Now let me remind you that we are looking for values of t in between ti plus 1. With that said, notice what will happen to n3i. n3i is only non-zero for values of t in between ti and ti minus 3. So this here is 0. How about this expression here? Now n3i plus 4 is non-zero for values of t in between ti plus 1 and ti plus 4. Now for those between ti and ti plus 1, this will again have to be 0. So we can erase the two terms, and the result will be n3i plus 1 of t plus n3i plus 2 of t plus n3i plus 3 of t. Can we use the same recursion relation to convert all n3s into n2s? Let's see. So n3i plus 1 is t minus t, I plus 1 minus 3 is I minus 2 over t I minus t I minus 2, and then we have n2 I of t plus ti plus 1 minus t over ti plus 1 minus ti plus 1 minus 3, which is I minus 2, plus 1, which is I minus 1, of nk. So this is n2 comma I plus 1 of t plus. Now let's see if this is correct. So t minus t I plus 1 minus 3, which is I minus 2, and then this is t I minus 1. So I plus 1 minus 1 is ti minus t I minus 2. This is n2 I plus 1 minus 1, n2i plus ti plus 1 minus t over ti plus 1 minus ti I plus 1 minus 3, which is I minus 2 plus 1, which is I minus 1. And then this is n2 I plus 1 of t. And then keep on incrementing the I in this expression. So we'll have t minus t I minus 1 over t I plus 1 minus t I minus 1. I'll have to be careful here. This is n2 I plus 1 t plus ti plus 2 minus t over ti plus 2 minus ti. This is n2 I plus 2 t plus t minus ti over ti plus 2 minus ti n2 I plus 2 t plus ti plus 3 minus t over ti plus 3 minus t I plus 1 n2 I plus 3 of t. Once again, we have this term common here and this denominator common here. And then we have n2 I plus 2 common here, and once again the denominator common here. Let's simplify this further. So if you look at these two terms, the coefficient will be 1 of n2 I plus 1, and likewise of n2 I plus 2, again the coefficient will be 1. So we'll have t minus t I minus 2 over ti minus ti minus 2 n2I of t plus n2 I plus 1 of t plus n2 I plus 2 of t. So we have n2 I plus 1 of t, we have n2 I plus 2 of t, and then we'll have this term here, which is ti plus 3 minus t over ti plus 3 minus ti plus 1 times n2 I plus 3 of t. Once again, let me remind you that we are looking for values in between ti and ti plus 1. Now n2I is non-zero in between the values ti and ti minus 2. Otherwise, this is going to be 0. So in this interval, n2I will be 0. Likewise, n2I plus 3 is non-zero in between the interval ti plus 1 and ti plus 3. So clearly, here n2I plus 3 will be 0. Let me get rid of these two terms to finally have in the summation n2I plus 1 of t plus n2I plus. Now let's convert these n2s into n1s using this recursion relation. Okay, so n2I plus 1 is t minus t I plus 1 minus 2, which is I minus 1, over t I plus 1 minus 1, which is ti, minus ti minus k, which is ti minus 1. And then we'll have in 1 I plus 1 minus 1 is I of t plus t I plus 1 minus t over t I plus 1 minus t I plus 1 minus 2, which is I minus 1, plus 1 is ti. We'll verify if this is correct. And 1 I plus 1 of t. So once again, I minus k is I plus 1 minus 2, which is I minus 1. Ti minus 1 would be ti plus 1 minus 1, which is ti, minus ti plus 1 minus 2 is ti minus 1. This is n1 I plus 1 minus 1, which is ni. Here we have ti plus 1 minus t over ti plus 1 minus ti plus 1 minus 2, which is ti minus 1 plus 1, which is ti, and 1 I plus 1 of t. And then simply increment the I here to get n2I plus 2t. So here we'll have plus t minus ti over t I plus 1 minus ti and 1 I plus 1 of t plus ti plus 2 minus ti, sorry, ti plus 2 minus t over ti plus 2 minus ti plus 1, incrementing this by 1 times and 1 I plus 2 of t. Okay. Now this is 0 for t in between ti and ti plus 1. This is 0 for values of t in between ti and ti plus 1 again. Note that this is non-zero for t in between ti plus 1 and ti plus 2. So this basis function doesn't bother us. We are left with n1I plus 1 here and 1I plus 1 here. Denominator is common, ti plus 1 minus ti, ti plus 1 minus ti. We can club these two terms together to get n1 I plus 1 times ti plus 1 minus ti this is ti plus 1 minus t plus t minus ti. So these t's cancel. The numerator ti plus 1 minus ti is the same as the denominator. So this would be 1. And so we are left with n1 I plus 1. And by definition, this should be a function of t. By definition, n1 I plus 1 is equal to 1 for all t belonging to ti, ti plus 1. It should be possible for you to show this for a generic case when you add p out of p normalized basis spline functions.